Greetings, fellow chemists. I am here to present 312 Hughes law with you guys. So for this experiment, we had to measure the amounts of heat released in these three related exothermic reactions. So the first one being solid sodium hydroxide dissolved in water. The second reaction being solid sodium hydroxide with dilute hydrochloric acid. And the third reaction being sodium hydroxide solution with dilute hydrochloric acid solution. After determining the heats of reaction, we then had to analyze our data and verify Hughes law. So for each reaction, we had different steps and procedures to go by. After following the steps and procedures, we then had to fill out our data table right there. Our data table consists of each reaction and their mass of NaOH, initial temperature, and the final temperature. So for the first reaction, the mass was 3.998. The initial temperature in Celsius was 25.01 degrees Celsius, the final temperature being 30.9 degrees Celsius. The second reaction, we had 3.9958 for the mass, 25.01 degrees Celsius for the initial temperature, and for the final temperature, we had 36.05. The third reaction, we had 0.400 grams, the initial temperature being 24.99 degrees Celsius, and the final temperature being 30.84 degrees Celsius. So for the next step, we had to determine the change in temperature for each reaction. So for that, we had to subtract the final temperature and the initial temperature for each reaction. So for the first reaction, we had to subtract 30.90 minus 25.01, which came out to be 5.89 degrees Celsius. The second reaction, it came out to be 36.05 minus 25.01 equals 11.04. The third reaction, we had 30.84 minus 24.99, which came out to be 5.85. And those were the differences for the change in temperature. So after that, we had to calculate the mass of reaction mixture in each reaction. So to do this, we had to first determine the total volume of the solution, then calculate the mass of the solution based on the assumption that the added solid does not change the volume and that the density of the solution is the same as the pure water, 1.0 grams per milliliter. So the mass of NaOH plus the mass of HCl equals the mixture mass. So what I did was 100 milliliters times 1 grams per milliliter equals 100. Then 100 plus 100 equals to 200 grams. Which leads us to the next step. The next step is to calculate the total heat release in each reaction in J's, assuming that the specific heat capacity of the solution is the same as the pure water, 4.184. So for the first reaction, we had to multiply 200 because of the 200 grams of the prior step times 4.184 times 5.89, which came out to be 49.28.75. The second reaction, we used 200 as well, and we multiply times for the 4.184, which is the pure water, of course, again, times the 11.04, which came out to be 9,238.27 J. For the third reaction, we had 200 times 4.184 times 5.85, which came out to be 4,895.28, which leads us to the next step to calculate the number of moles of NaOH used in reactions 1 and 2. So for that one, we have the mass, which was 4, and the NW, which came out to be 40. Then we divide 4 divided by 40, and it comes out to be 0.1 grams per mole. Then that leads us to our next step, where we calculate the number of moles of NaOH used in reaction 3 by multiplying the volume of NaOH times the molality, which is 1.00 moles per liter. So what I did is I multiplied 1 times 1,000 over 1,000, and that came out to be 0.1 moles as well. Which leads us to our next steps. And the next step is to calculate the energy released in kJs. So for the first reaction, I inputted 4,928.75 divided by 3.99839 divided by the 40, which came out to be 49.31. The second reaction, I inputted 9,238.272 divided by 3.9958 divided by 40, coming out to be 92.48 kJ per mole. The third reaction came out to be 4,895.28 divided by 4.009 divided by 40, and that one came out to be 48.94 kJ per mole for the third reaction. So for the results table, we had to input our results that we found in the previous steps, and for the next step, we had to show that the equations for reactions 1 and 3, which are given in the background section, add up to the equation for reaction 2, and we had to include the energy release per mole of NaOH in each equation. So what I did was right here was add energy 1 plus energy 2, which is 49.31 plus 48.94, which came out to be 98.25. So the second energy came out to be 92.48. So then we have to calculate the percent difference between the heat given off in reaction 2 and the sum of the heats given off in reactions 1 and 3. So we had to assume that the heat given off in reaction 2 is correct. So here's the formula for us right here. So we have the percent difference, then we have the heat 2, the heat 1, and the heat 3 over the heat 2 times 100. So after inputting all the inputting the formula, I came out to the conclusion that it's going to come out to be 92.48 minus 98.25 over 92.48 times 100, equaling to 6.24%. So that is the percent difference. So then for the final question, we had to state in our own words what is meant by the additive nature of heats of reaction. So in my own words, I input that heat in one reaction will be the same to the heat by all other reactions. And with our steps and procedures, we were able to obtain the same enthalpy value. And that is my lab. Thank you.